One of the longest and most important debates in the history of science concerned the nature of light. The debate began in the mid-16th century and didn't end until the early 18th century. When we finally understood the nature of light, it led to the invention of radio, television, cell phones, microwave ovens, X-rays, and devices that are used to sterilize our food and drinking water. In the 17th and 18th century, there were two competing theories about the nature of light. One theory said that light acts like a wave in its interactions, and the other said that light acted more like a particle. The debate raged on for more than 100 years, and very prominent physicists were on opposite sides of the debate. In the early 19th century, an experiment finally convinced scientists that the wave model of light was the best explanation for light's behavior. To support their theory, the proponents of the wave model of light pointed to light's behavior when it passes through a small opening. When the light on the left leaves the small opening in the barrier, it spreads out. This wave phenomena is called diffraction. In a similar way, it is the diffraction of sound waves from your vocal cords leaving your mouth that explains why your voice can be heard everywhere inside a large classroom. While diffraction is in fact a phenomena that could only be explained by the wave theory, for reasons that I won't get into, it was not enough to end the debate. According to the proponents of the particle theory, if light were actually a wave, it would have to do all the things that waves do. For instance, when two waves overlap, the energy of the two waves can combine constructively or destructively. The video shown here is an example of constructive interference. In this kind of interference, the energies of the two waves combine to form a single wave that is the vector sum of the component waves. If light showed a wave behavior, not only would you need to show that light acted constructively, but you would have to be able to show that two light waves could overlap destructively. The animation above shows total destructive interference. If light were truly a wave, it should be possible to show two light waves overlapping to produce darkness. That was the big experimental challenge for the wave theorists. Until this experiment was performed, the debate would continue. You've just heard an example of two sound waves spreading out and overlapping constructively and destructively. The constructive interference and destructive interference creates the rapidly alternating loud and low sounds. Constructive interference creates the loud sound, and the low sounds are caused by destructive interference. Let's review wave interference. Constructive interference occurs when a crest meets a crest and when a trough meets a trough. Destructive interference occurs when a crest meets a trough. In 1801, the British physicist Thomas Young passed a single source of light through two tiny slits and produced an interference pattern that proved that light had a wave behavior. The thin black lines in this picture show destructive interference, and the bright lines are produced by constructive interference. This picture shows the overlap of two wavefronts. The blue dotted line shows constructive interference, and the red dotted line shows destructive interference. Constructive interference occurs at A, B, D, and E, where crest meets crest and trough meets trough. Destructive interference occurs at C and F, where crest meets trough. The interference pattern of bright and dark lines spread out when the slits were closer and came closer when the slits were moved apart. Whenever light passes through a pair of slits, a constructive line appears in the middle. We call that line the central maximum. The lines on either side of the central maximum are called the first-order bright lines. When Young changed the color of light, he noticed the space between these lines changed, with red creating the largest spacing. Further investigation revealed that violet created the smallest bright line spacing, which indicated that violet has the smallest wavelength and red the largest. In the upper middle of this slideshow, you'll see the interference pattern of green light. Let's review what you've learned about the interference pattern created when a single source of light passes through a double slit, spreads out, and overlaps constructively and destructively. Constructive interference causes the bright lines, and destructive interference causes the dark lines. Let's use this animation to understand why light from each slit produces a bright line in some places and a dark line in other spots. Light from each slit travels the same distance when it hits the middle of the screen, so the waves are identical and overlap constructively, When the difference between the path that the light travels is 0 or a whole number, you get constructive interference at that spot. The first order bright line occurs when the path difference is 1 wavelength. The 2 dark lines on either side of the central maximum are a result of a path difference of 1/2. This is the end of my presentation on the wave behavior.